Hello everyone, back at another exponential logarithmic function application. This one you're given a formula which is the standard exponential growth formula considering continuous growth, but instead of calling it p equals p sub 0 e to the rt or a equals p e to the rt, the PERT formula, you may see different variables. But so understand that the exponential model at hand, when you're talking about exponential growth or decay, is your amount present is always the initial amount times, in this case it's base e, it could be another base, a base to a rate times time exponent. You've seen other problems where this could be any base. That's the general flow of the formulas. So this says 80% of a radioactive material remains after 40 days. Find the decay constant, K, in the exponential model. N equals n subscript 0, e to the kt power. And to maintain accuracy, enter a symbolic exact answer and not a decimal approximation. Okay, using the formula that you're given for this first part, what you know is that when t is 40 days, the amount n is 80% of what you started with. And if you use this fact, sub in here for n and for t, you can notice something that's consistent with these types of equations in exponential growth decay, that the initial amount cancels. We're left with the equation 80%, or 0.8, is e to the power 40k, which I then personally go directly to the definition of the logarithm, which is the exponent is log base e of 0.8. So the decay constant is natural log of 0.8 over 40. Now, I'm not going to do this in the box. I'm going to put natural log of 0.8 over 40 because I said I could leave an exact or a symbolic answer. But I want you to notice what this is as a calculator value. It's approximately negative 0.00558. And the point I'm making here is that it is indeed a negative rate. So that's consistent with the problem being a decay problem. All right, so now we have settled the value of k is natural log of 0.8 divided by 40. The second part of the problem says find the time t in days after the initial measurement. So when we took the value and measured n sub 0 at time 0, when 44% of the radioactive material remains. Okay, so I'm going to ask the question down here. When will 44% of what I started with remain? And the when question, of course, means that I am solving for time. So this is basically actually to even be more descriptive here. The amount remaining is capital N. So when will capital N be 44% of n sub 0? So I want to solve the equation 44% of n sub 0 equals what my formula normally gives me at time t. Now I'm going to do this. This is my little deal. I'm going to put a circle around k. I know k. It's over here. Maybe I'll even put a red circle around it. I'll insert it at the end of the problem so that I don't have to keep writing it. Okay? So notice n sub 0 cancels from each side. And we have the value 0.44 is e to the k that I know, t power. So the definition of a logarithm, just like before, says that the exponent is the logarithm base e of 0.44, and we've been, as we did earlier, writing logarithm base e with the shorthand notation, and I wrote it as I said it before, but let's do it here. Natural log of 0.44. Okay, so again, to emphasize, log base e and the symbol ln, same meaning, second one's an abbreviation. And then we solve for t, which is natural log of 0.44 divided by the value of k, which we found in an earlier step was natural log of 0.8 itself divided by 40. Okay, so this is the time in t days. And now let's scroll back up just briefly. It says you may prefer to enter a symbolic answer. When that is the case, these guys are perfectly acceptable. Those are exact symbolic answers. But if you want a number crunch to check yourself, it'll certainly help you to make sure, for example, that you don't get a negative time. That wouldn't make sense. And so definitely double check yourself when you're doing your homework. But I hope that you see that, again, what we had was a basic exponential model. The amount present at time t is the initial amount times a base, in this case, which was given to us, e, to a rate, time power. And we were able to navigate through this problem by knowing where to substitute the values we were given and then how to solve a basic exponential equation.